All right, so gravity. This will be the first of the four forces that we introduce, and part of the reason that we're introducing it is because what we're going to be talking about next, which is fluids, gravity plays a role in some of the fluid equations, and so we might as well cover gravity coming in. But in general, fluids, you don't even necessarily need gravity to talk about fluids the same way that we've talked about the other things. All it is transferring what we've learned in physics from that corresponds to individual particles and expanding them to continuous media that has mass and that has can have velocity and so forth. And so fluids is basically, like I said, it's expanding the point particle approximation to everything that we've discussed into a continuous medium. But in the meantime, we want to cover gravity so that we can include that in those things. So gravity is what we're going to be talking about today. And all right, so there we go. Gravity is one of the four forces. We mentioned before that the four forces are, where did my thing go? Electromagnetism. We've got gravity. We've got the strong and the weak forces. Weak is spelled this way. And all four of these forces, there is a charge associated with them, and there is a field that is produced by that charge. So the charge sources the field, and the charge also responds to the field that's in the environment. Those two are related to each other the same way that for every action there's an equal and opposite reaction. Charge produces a field. That charge also responds to the fields produced by other charges in the area. Charge is simply the coupling that force or that particle has to the field in question. So with the electromagnetic field, it's electric charge. With gravitational field, it's the mass or the energy. I mean, it's the energy, but we're going to go with mass because that's the limit that we're taking in this case. The strong force, this was the color charge, and the weak force was the weak isospin. Okay, and each of these forces produces a field that's proportional to each of these things, and any particle that has this charge on it, that is painted in that charge, or has the property, some property of that charge, is going to couple to that field, and as a consequence, it will have potential energy based upon how that field is, the structure of that field in the location where that particle is located, which is a great way of completing a sentence. So if you're at some location, there's some ambient field. If you have a charge that couples to that field, then you'll have potential energy. The field, again, here is the electromagnetic field, which is photons, basically, light. For this, it's a gravitational field. For the strong nuclear force, it's the gluon field. And for weak isospin, it's the W and the Z fields. So these ones we will talk about a lot later. E&M we'll talk about in a couple months or so. Gravity is what we're going to be talking about today. So it has a charge that is, at least in this case, the mass, and it has a gravitational field associated with it. Fundamentally, if quantum gravity is a real thing, then it would be the graviton, but until then, it's just the gravitational field. All right, so what does this mean? Well, this is a source of potential energy. Because gravity is a source of potential energy, you can have some gravitational field. That field is going to couple to whatever particles have mass or energy. Those particles are going to recognize the fact that there is a gradient to that field in some location, and as a consequence, they will feel a force exerted on them proportional to the slope, how steep that gradient is. So this could be the gravitational field as a function of position. And if you have an object up here, it's going to say, oh, there's a gradient in the gravitational field that's going to drive me in this particular direction, and it will convert the potential energy into kinetic energy as it rolls down this hill. The magnitude of the gravitational field, I'm not sure what you're referring to here. This is the potential of the gravitational field, and the energy that you get is that potential. Maybe phi is a better thing to use, but we'll use V since it's already written up there. Is going to be m times that. Okay, so what does the gravitational potential actually look like? If you have a point like mass, it looks like this. So the gravitational potential, I'll switch to phi, or not, I'll keep it with V. Gravitational potential is going to be Newton's gravitational constant times the mass of the particle whose field that's producing the field divided by this, gm over r. I think there's a minus sign. Is there a minus sign? So the gravitational field's like this. I don't think there's a minus sign. So it's like this, and then that way the force gives a minus sign. And and that indicates that the force is always attractive. So this is the gravitational potential for a single point-like particle, and then you bring another particle with mass next to it, and then you get m times v, which gives you this is the potential energy. So this is the potential. The potential energy is the coupling, like the charge coupled to that field, and that's going to be gmm over r, and then the force is the gradient. The force of this is going to be the gradient of this with respect to, in this case, r, and that gives you the minus. So the gradient of this is the slope of that curve is going to be minus gmm over r squared, and that is the gravitational force that everyone knows and loves. Let's see, to find the mass, momentum, and angular momentum of the graviton is to find the asymptotic behavior of the Minkowski metric field. That sounds like a good idea to me. General relativity is not something that I've studied in any great detail. I know enough to be dangerous, but I don't know enough to really get into the details of it. All right, so a few things about gravity. Some of this was learned by Galileo a long time ago, is that things of different substances, if you have two objects that are made out of different stuff, so this could be made out of wood and this could be made out of metal, they will fall at the same rate. And that's something that's interesting. This is something that's also encapsulated in Newton's formulation for the law of gravity. So Newton's formulation of the law of gravity was basically that potential that I just showed, except you convert it into a force, which is that you take the gradient. The force of gravity is equal to gmm over r squared. So this is the force of gravity between two different objects of masses here and here, separated at this distance, and g is the constant that converts you from the charges and distances into the units of a force. So this is the force of gravity that Newton devised, kind of from first principles. It was suggested to him by Halley, like Comet Halley, that maybe there's a force that looks like this, and then you take this is a force, it is not a law of nature. So there are some teachers who'll be like, oh, this is like Newton's fourth law of motion, or Newton's fourth law of, fourth law of motion, which it is not. It is not a fourth law of motion. This is a force. It's a force, and therefore it goes into Newton's second law, which is that forces cause masses to accelerate. So this is a force. It is not a law of motion. Laws of motions are how do you translate the interactions that something has onto your particle that's moving in some kind of coordinate system. And this is a force, which is one component of one of the laws of motion. It goes in right there. Okay, so what does this mean? If we take these things and put them all together, what does this mean? According to Newton, Newton's law of gravity, gmm over r squared is going to be the mass of some object times the acceleration of that object, or the change in momentum. Remember that this is the change in momentum with respect to time. The weird thing is that this mass here cancels with this one. This is fact that these two things cancel is written into the theory. It's written into Newton's theory. It's not something that would necessarily happen from the get-go. There's no reason that the charge that creates the gravitational field should equal the mass that is pushed around by that field. Okay, it's one thing to have, so this is the resistance that an object has to a force acting upon it. It's the m that goes into the quantity of motion, into the momentum. It's this m. That is a property that something has that's fundamentally related to its coupling to the Higgs field. It is not, in principle, the source of one of the forces, except it turns out that it appears to be the case. There's no reason that it should have been the case. However, it is the case for the force of gravity, that this m here is exactly equal to this m here. Now, that is, of course, something that you would test. You'd want to test this with some experiment. It's called the equivalence principle. Like that. The equivalence principle is the principle that the mass that gets pushed around by the force is exactly equal to the mass that causes the force to begin with, for the case of gravity. That's the equivalence principle. What does this mean? What this means, since these two masses are equivalent, you can divide both sides by that mass, and you're left with an acceleration. So here's your acceleration that is independent of the mass of the object that is being accelerated. Okay, so you have two objects. You put them in a gravitational field. The mass of both of those objects will cancel So you have two different objects, which means they each have their own equation of motion. You put them in this gravitational field, you let them both go. The equation of motion for both of them is going to be that the acceleration is proportional to the ambient gravitational field and not to the mass of the particle that's being accelerated by it. And so the equivalence principle, that is something that's not common to all the forces. And this is something that people have been testing ever since Galileo, even starting with Galileo, where you take two objects made of different stuff, you drop them both down, and you see which one lands at the bottom, lands on the ground at the first, and it turns out that they landed at the same time. If you have, let's compare this to the electromagnetic force. So the electromagnetic force is that you have, the electromagnetic force is equal to the charge on two objects. There's a constant out front. There's the electric charge on the two objects, and then there's a distance between, separating your two objects. That is a force. You compare that to the force of gravity, and you get G(m)(m) over r squared. And then you put this in to Newton's second law. So that's going to cause the mass to accelerate. This is also going to cause some mass to accelerate. For the case of the gravitational field, the masses cancel, and you get that the acceleration is equal to G(m) over r squared. So this is little g at the surface of the Earth. So that's the 32 feet per second squared, or the 9.8 meters per second squared. That is this, and that is a consequence of the fact that these two masses cancel, the inertial mass on this side and the gravitational mass on that side. So the gravitational mass is the mass that causes the field to exist, or I should say, the gravitational mass is the strength of the coupling that an object has to the gravitational force, and the inertial mass is the resistance that that object has to being pushed around. So gravitational mass and inertial mass, the fact that those are the same is the equivalence principle, and is what causes everything to accelerate at the same rate, independent of the mass that they have, and as a consequence, independent of the composition that they have. They can be made out of anything. For the case of the electromagnetic field, these things don't cancel. We get an acceleration here that is kq over r squared, and then we have this q over m out front. This is the charge to mass ratio. So it tells you how strong the coupling is that that object has to whatever the field is, and how hard is it to push that around. So for the case of the gravitational field, the charge to mass ratio, which is m, like the inertial mass charge, would be the gravitational mass over the inertial mass. So this would be the inertial mass, and this would be the gravitational mass. So again, the gravitational mass is the strength of the coupling that the object has to the gravitational field, and the inertial mass is the resistance that the object has to being pushed around. So for the case of gravity, these two things are equal, and so that's going to be 1. For the case of all other forces, they are not equal, and you get the charge to mass ratio. So this is, that's the difference between something that satisfies the equivalence principle and something that does not. One of the consequences of this, for example, is that you can take two objects of identical mass, but with different charges. So this one could be positive, this one could be negative, and you put them in an electromagnetic field. Instead of a gravitational field, you put them in an electromagnetic field, and you let them go, and they will move in opposite directions. If you take a proton and an electron that have exactly the same charge, you put them in an electromagnetic field, and they will go in opposite directions and at totally different rates. The proton will accelerate 2,000 times slower than the electron will, because the electron is 2,000 times less massive than the proton. And so the electromagnetic force does not satisfy the equivalence principle. You take these two things, you put them in a gravitational field, and they will move in opposite directions, where gravity does satisfy the equivalence principle, and everything accelerates in the same direction at the same time. Now, I have a video that I've already done where I kind of investigate what are the tests that you can make of the equivalence principle, because this, simply claiming the fact that the mass over here that gets pushed around and the mass over here that couples to the gravitational field are equal doesn't actually make it so. And so there are a variety of tests that you can do with torsion pendula in particular, but also just looking at the orbits of the moon, where you put in objects of different compositions and you see if they actually do accelerate at the same rate towards whatever your object is, or whatever your field is. So if you look at, so this is an example of one of these torsion pendula. Let's see, open it in a new tab like this. That's not what I want to do. Okay, I guess we'll just go like this. So this torsion pendulum, it's suspended by a thin fiber. These bulbous appendages that you have on there are made out of different materials. So they're different materials that have essentially the same density. It's an alloy. One of them's an alloy, the other one is a pure substance. But they're designed so that they have the same density, so you can make them exactly the same shape, but they have different amounts of protons and neutrons in them. So some of them are more neutron rich, some of them are more proton rich. And so they have slightly different compositions. And then you can say, because these things are made out of different materials, they might accelerate differently, because maybe gravity couples slightly differently to protons than it does to neutrons. That would be this test, because you have a different amount of protons and neutrons between these different objects. You have them twisting, you put them, suspend them via fiber, and then you have it twist in the presence of some ambient gravitational field, and you look to see if it accelerates more strongly, or if the coupling is stronger between the neutron-rich material compared to the proton-rich material. And so far, the answer is no, that the coupling is exactly the same in all cases. But this is an example of a test that you can run. There are other tests that you can run. For example, the Earth and the Moon don't have the same composition. So the Moon's composition is more like, okay, so here's the Earth. The Earth has this iron core, and it has this rocky mantle. The Moon is basically made out of rocky mantle material. It's essentially the same composition as the outer layers of the Earth, but not the inner layers of the Earth, not the core. And so what you can do is, here's the sun, and you have the Earth and the Moon out here, and you can compare how the Earth and the Moon accelerate towards the sun. If, for example, iron accelerates at a different rate than silicate olivine minerals, then you would show up in a difference between the orbit that you would predict otherwise. So the orbit that the Moon would have around the Earth, if it has a stronger or a weaker coupling to the sun, will be different than if it has a coupling that's exactly the same towards the sun. And so the way that this is done is the most recent program was called Apollo, which is Apache Point Observatory Lunar Laser Observatory. Those last two words, I know it's lunar laser. I think it's Lunar Laser Observatory. There might be some other word in there that I'm missing. But anyways, Apache Point Observatory, Lunar Laser Observatory. What they do is you have the Moon up here. The Moon has some retroreflectors. We can see what the lunar retroreflectors. Okay, so these are the retroreflectors. They're basically corner cubes, so that when light comes in, it bounces around and shoots straight back out the way that it came in. The same way that, so there's this is kind of an interesting aside. If you take a cube like this and you slice it off like that, so that you have just a corner of that cube like this, then light that comes in from any angle will bounce around in there, and it will come out at exactly the same direction that it went in. So it'll come in at a given angle, and it will bounce out at exactly the same angle. That's what the corner cube does. And so when you have reflectors on a bicycle, it will have little tetrahedron type structures on it. Although they're 90-degree angles on all these things. That's how you design bicycle reflectors, so that any light that hits the reflector, it doesn't matter. It's not going to bounce off in some random direction. It will bounce straight back towards the light that emits it. So that way, when you're driving down the street and your headlights hit the retroreflector of the bicycle in front of you, it will always bounce back straight to your eyes. And so that is what's going on in these. There's little corner cubes in all those. So like this one, that's what they look like on the surface of the Moon. And then you have this Apache Point Observatory on the Earth. So here's the Earth down here. You have a telescope. Okay, that's an ugly telescope. Let's draw a better telescope. So you have your telescope like this. You have your laser beam like this, and you have the Moon up above you. And so you shoot your laser beam up, bounce it off the Moon, and comes back down to the telescope, and you time the pulse, your laser pulse, when you send it off to when it comes back. And that gives you the distance to the Moon. So they can measure the distance to the Moon, or the distance to the surface of the Moon, to within like a centimeter from the light travel time, which is pretty good. Then what you have to do is you have to say, all right, I now have the position of the Moon over and over and over and over and over again. I'm mapping out the position of the Moon. Thank you for that sub. I appreciate that very much. You trace the position of the Moon and get a really accurate model or plot of the location of the Moon as it orbits the Earth. then what you can do is compare that to what you would predict from gravity, the gravitational theory. Does it follow Newton's laws of motion? If it does follow Newton's laws of motion, then a consequence of that is that you get GM. It implies that these two things actually do cancel, because Newton's laws of motion, when you put in the gravitational force, those two things exactly cancel each other. However, if there's some deviation, then that would imply that there is a slight difference between the mass that sources the gravitational field and the mass that is accelerated by that gravitational field. The challenge is that not all of these objects, the moon and the Earth, they're not all perfect spheres. The Earth has this bulge of water that's attracted towards the moon. The continents slam into it. The sun distorts the shape of the Earth. So the Earth is actually not the Earth is not a sphere. It's not flat, but it's not a sphere. It's kind of a pear-shaped. It's primarily an oblate spheroid, but it also has a pear shape where it's a bit fatter around the southern hemisphere than it is around the northern hemisphere. It's not quite this bad. There's a thing called the Earth. Is it the Earth geode? Earth gravitational field. That's what it looks like. So some places it's got a stronger gravitational field than others, depending upon what's near the surface and stuff like that. So the Earth is not a perfect sphere, especially when it comes to the gravitational field it emits. And so now you have the moon that's going through this varying gravitational field, because you might have, for example, a tall mountain range, like right here. Here's your tall mountain range. It's going to have slightly stronger gravity because it's made out of heavier stuff than, say, the middle of the Atlantic that's just made out of water. Rocks are heavier than water, at least, except according to Monty Python. But for everybody else, rocks are heavier than water. Even very small rocks won't float in water. And so the water has a smaller density, and as a consequence, it will have a smaller gravitational field than you would in this area. So now you have all these features on the surface of the Earth, and that's going to change the orbit of the moon as the moon goes around. And at some point, those effects could change the position of the moon by something of order 1 centimeter. And so what happened with this Apollo APO Lunar Laser Observatory is basically they got data as precise as their model for the gravitational field of the Earth would allow. Because even if you have an earthquake, it changes the shape of the Earth, and it can cause a measurable change in the moon's orbit around it. The upshot was that as well as they could model the gravitational field of the Earth, including weather patterns, as well as they could model the gravitational field of the Earth, the moon followed the predicted path, and the equivalence principle was satisfied. So if I take a look to show you just how good of a job they did at saying, yes, the equivalence principle does apply to the moon's orbit, that those two masses do actually cancel. So this shows you the deviation, like how much the equivalence principle could be violated and still be consistent with the measurements that we make. So the question is, does this mass over here and does this mass over here actually cancel? And how much do they cancel? How much error can be left over if we pretend that they cancel, but one of them is actually 1.00000001? How big can that decimal point be? And this is the answer. So at laboratory scales, the bottom here is cut off for some reason. It doesn't have the information down here. I know that this is at 10 centimeter scale right here, and this is at millimeter scale. No, this is the 10 centimeter scale, and this one is like a 10 meter scale. So we're looking here so 1 meter is basically this distance right there. So that's 1 meter. This would be 10 meters, 100 meters, and so forth. And the lunar laser ranging, that is the best constraint that we have on deviations from the inverse, or deviations from the weak equivalence principle. So the thing that those two masses cancel. So we know that the gravitational mass and the inertial mass, at least at certain distances, can be no different than a part per 10 billion, which is what? It's 10 parts per trillion, or 100 parts per trillion. So that's from the lunar laser ranging. That's the best we can do. And we're limited by the model that we have for the gravitational field of the Earth and the effect that tides and stuff like that, the tides from the sun, have on the shape of the Earth. These ones are based upon planetary orbits. This one is based upon the Lagos satellites that are orbiting around the Earth. Here's the Earth Lagos. It is how it affects the moon. So Lagos is a series of, so these are satellites that are put up in orbit around the Earth that also have retroreflectors, like that have the corner cubes that will, if you shoot them with a laser beam, it will come directly back at you. So that's what those results are related to. And then you have stuff, geophysical is like the gravitational field from the oceans, and you measure it with salt water and submarines, and there's one with radio towers and things like that. Anyways, but again, it shows that the best constraints are the ones that we got from bouncing laser beams off the surface of the moon and testing gravity. It does look like a disco ball. That is indeed true. Let's see. Can you talk about how to read gravity and magnetic maps of the Earth? Depth measure, or is it topography related? So this gravity, this thing that I showed, not here. Do I still have it up here? I don't think I do. So the Earth's gravitational field, this thing, this is measured basically with, probably measured with satellites. You can measure a local gravitational field with a gravimeter. You just have some object that measures the local acceleration. You can use that to, for example, if you have a pocket of, here's the Earth, you have the crust, and then you have some blob of oil underneath the surface. The gravitational field, rock is heavier than oil, and so if you have your gravimeter at this location, you'll get one acceleration due to gravity, and if you walk over here, it will get weaker because the density is lower. If you're over the ocean, so if this is the ocean and you're over here, the gravitational field again will be weaker. And so it's one way of finding caves or oil deposits or something like that, is that you change the local density, and as a consequence, you change the local acceleration due to gravity. All right, so that is the equivalence principle. So that tells us what's going on with, we've tested this theory of gravity that Newton devised, which is G, that the force of gravity is Gm, big M over R squared. We've tested the equivalence principle because Newton says this is what goes into the force of Newton's second law, and this is what the consequence is, and Newton also claims that this mass here should cancel that one there. That's the equivalence principle. That's been tested on a variety of length scales in the laboratories. So far, it's withstood every test, but that doesn't mean that it's necessarily true. We could find deviation. It just means, that it's useful to continue conducting the kinds of experiments that will test that. Another thing that's interesting that one could test is this one right here, the fact that this is actually the inverse square law. I was on a pendulum, a similar experiment, a torsion pendulum experiment that was specifically looking at violations of the inverse square law. Maybe it's actually not r to the minus 2, like 1 over r squared. Maybe it's 1 over r to the 2 point something, something, something. Or maybe it's it actually has some potential that looks different, that is like either the minus r over lambda, Gm m over r, that this is the potential, and then you take the gradient. So it's actually a consequence of this is you get something that's slightly different than the inverse square law, because you have to take a derivative, the slope that includes this little exponential term. So anyways, all these different kinds of tests are also done. Does this actually work? Is this the right thing? Does big G, is this really a constant? Maybe big G changes depending upon, for example, maybe big G changes in time. All these things are testable assumptions that go into Newton's theory of gravity. So there are tests of big G, how much it can vary with time. There are questions, maybe big G changes based upon how dense the environment is. All these things are stuff that we can test. Okay, so that's basically the force of gravity, and it goes into the Newton's second law. There's other things that we're supposed to cover in this chapter. Let's see. So a few things. Number one, gravity, the force of gravity is always attractive. So whenever you have an object here and an object over here, they will always attract each other. This is not the case with the electromagnetic force. The electromagnetic force has both positive and negative charges. And so the electromagnetic force can be both attractive and repulsive. Gravitational force has only positive charges. And so the gravitational force will always be attractive regardless of the kinds of objects that you put in. There may be something weird going on with dark energy, but that assumes that dark energy is actually a gravitational phenomenon and not a phenomenon from some other quantum particle. That's something to be discovered in the future. With the fact that the gravitational force is always attractive, that there's no negative charges, like no negative mass, that actually implies something really interesting. And it tells us why ultimately gravity wins. So you have a black hole, for example. So here's your black hole. You put stuff into it, and gravity will win in that case. It doesn't matter what other forces you try to prevent the collapse. There's some other force that you're trying to push away from the surface of a black hole. Nothing will win. So for example, when you have a neutron star, that's supported by an intense pressure coming from the quantum states of the neutrons in it, that is not enough. The strength of the strong nuclear force that's keeping this thing kind of in solid state is not sufficient to prevent it from collapsing if it gets too big. So gravity ultimately will win over the strong nuclear force. It will beat the weak nuclear force. It will beat the electromagnetic force, even though on the surface of the Earth, the gravitational field is the weakest of the forces. The gravitational field of the Earth is not that strong. Here's this thing that I have, or a pen. Here's this pen. I can take this pen and with my hands, with the electromagnetic force that I can generate with my hands, because my hand's got these electrons in it, and the pen has these electrons in it, and it's pushing, I can push against it. My puny little arm is able to overcome the gravitational field of the entire planet of the Earth. Okay, if I was on the surface of Jupiter, that's 300,000 times, or 300 times bigger than the Earth, 300 times more mass than the Earth, I would still be able to lift this pencil. I can lift this pencil against the entire planet that's conspiring to try to pull it down. That's an indication of how weak the gravitational force is relative to the electromagnetic force. And so, but then the question becomes, why in the end then can gravity win? Why does the electromagnetic force fail in the presence of a gravitational field from the black hole? And the answer to that question is the electromagnetic force has both kinds of charges. And so you can build up, if you build up a bunch of positive charges in some area, these are all plus signs, it will attract a bunch of negative charges in the same area and become electrically neutral. You cannot do this with the gravitational field. You can't have a mass here and then hide that mass by putting negative masses around it. And so because the gravitational force is always additive, eventually you can build up enough gravitational field to overcome everything else. So just the fact that there's no negative mass means that gravity ultimately is the victor when it comes to its competition against these other forces. Let's see, does gravity have a direction without a frame of reference? That's a great question. So gravity, you always can draw, if you have two objects that are interacting with each other with the gravitational force, there's always going to be a line connecting them, because any 2 points are on a line is the postulate from Euclid. So you have this object here at some location. You have a coordinate system. So you know here's your arbitrary coordinate system. It's got some location here. You have another location up here with the other object. You can always draw a line connecting those two. And so it doesn't matter what the coordinate system is that you have to explain this, like the orientation of the coordinate system or where the origin is located. You can always draw this line and get that direction and that distance. And so the result is that the universe doesn't care what we assign as the coordinate system to these different things. And so the direction that you have depends upon like which direction the gravitational force is acting depends upon which mass you care about. Do you care about the motion of this object? Do you care about the motion of this object? And so which direction the arrow points is based upon which object you're trying to describe. Okay, so gravitational force, it's always attractive. As a consequence, you'll have objects that will accelerate around something with centripetal acceleration. Centripetal meaning center seeking. It's a force that's always pulling in towards the center. And then what I described early on is that if you have with circular motion, it's always seeking towards the center. There's no such thing as a centrifugal force, and there are fictitious forces that come when you assign yourself to a coordinate system that is accelerating. So I guess I'll go through it instead of just claiming that I've done it already. So going back to this idea of here is a curve and you have a bus and you're driving the bus around the curve, and you are a person that's inside this bus and you have a friend that's next to you. When the bus starts making this curve, you feel like you're being thrown outwards. You feel like, oh, I'm being thrown up against the wall. But that is not actually what's happening. What's happening is you are moving at a constant speed in a straight line in that particular direction. The bus is turning with respect to you, and so eventually you smash into the side of the bus, and the bus pushes you towards the center. So it feels like you're being flung to the side of the bus, but in fact the side of the bus is coming and cutting you off and pushing you towards the center. And then your friend starts to squish you up against the side, and so you're both squished up against the side. And you say, oh, that's a centrifugal force, centrifugal force, but this is fake. The centrifugal force is a fake force that arises because you are, in this case, when you're inside the bus, the typical reference frame that people have when they're inside the bus is forward. Like the forward direction is towards the front of the bus. And so the forward direction over here is in this direction. The forward direction over here is in this direction. And so you feel like you're moving with respect to the forward direction. You're moving to the side relative to the forward direction. That's a consequence of the fact that this coordinate system is accelerating, in this case, what direction is that? Counterclockwise. So this coordinate system is accelerating, but if you have an accelerating reference frame, then you don't have a reference frame where Newton's laws apply, right? Newton's 3 laws of motion are that an object in motion will stay in motion at a constant speed in a straight line unless acted upon by an outside force. That's a statement that Newton's laws only apply when you have a reference frame that is moving at a constant speed and in a straight line in some direction. And then an object at rest can stay at rest. So those are basically statements about you can choose your origin, you can choose your directions, but the motion of your coordinate system needs to be constant and in a straight line in order for Newton's laws to apply. If that doesn't happen, for example, if you accelerate your reference frame or if you rotate your reference frame, then Newton's laws no longer apply. So the way that we treat this is we say, okay, let's just say that the acceleration, the motion of our coordinate system that is not in a constant speed in a straight line, the accelerated motion of our coordinate system, we will call it an outside force. So they're called fictitious forces. To use fictitious forces, so fake forces, are the forces that we perceive when we live on an accelerating reference frame. So when you have an accelerating reference frame, the traditional way of treating it is to say, let's pretend that it's a Newtonian reference frame. Let's pretend that it's a constant speed, straight line type reference frame. But we will add these outside forces that come from the fact that the coordinate system is actually accelerating instead of ourselves. Centrifugal force is a fictitious force that arises because of the rotating reference frame of this bus as it goes around the corner. There are two other forces that do this, the Coriolis force, so that one was mentioned, and then the other one has a variety of different names. I learned it as the transverse force. So the centrifugal force, the one that pushes you out, is a fake force. It only comes because of the rotating reference frame. The Coriolis force is another one that does exactly the same thing, and the transverse force is a third one. So how these things are related to each other, so the centrifugal force, it basically comes down to you have a rotation of your coordinate system like this, so that's your angular rotation of the coordinate system, which is an acceleration because it's changing the direction, what direction forward means. So one of them, you have omega and you have r, and you have to come up with different ways of accelerating things. One of them is you can have an omega dot. So you need to come up, in order to make an acceleration, you need to have meters per second squared. And all you have to work with is omega, the rotation speed, and you have the distance between you and the center, like where you're located relative to the rotation. So it looks like meters per second squared. We have r, and we have omega to work with. Omega is the angular velocity, how fast the object is rotating. R is the distance that you're rotating relative to your coordinate origin. And you can change these things with time. So you can accelerate. Acceleration of the rotation rate would look like omega dot, and the acceleration of the distance, so like a changing distance, would be r dot. So you can make an acceleration by either having r omega squared. You can have the acceleration by being r dot times omega, so that means you're changing your distance relative to your coordinate, like to your origin, like your rotation axis. And the other one is to change the rate of the rotation, how fast you're rotating. This one is the centrifugal. This one is the Coriolis, and this one is called the transverse. Okay, so how do all these things compare? Well, the centrifugal one is weak when the rotation rate is small. So if rotation is very small, then this is a weak force because the value of the rotation rate, for example, with the case of the Earth, it's 2 pi over 24 hours. The Earth rotates in 2 pi basically in 24 hours, which is really, really, really slow. And so that means you take a small number and you square a small number and you get a really, really small number. So we don't experience the centrifugal force on the Earth. You have to have huge amounts of very spread out material in order to experience the centrifugal force. So the Earth itself, or the oceans, experience the centrifugal force, and it causes the Earth to flatten into an oblate spheroid. So the centrifugal force, it does cause the Earth to bulge out towards the center, but it's a relatively small bulge, and we don't experience this force. If, on the other hand, you crank on this omega, crank on the rotation speed, then you can get very strong centrifugal forces, strong enough to pin yourself up against the wall of a ride at an amusement park, and they can lift you up and spin you around and stuff like that. Coriolis force is what you get when you're changing your distance relative to your rotation axis. So here's a merry-go-round like this. Here's you standing on this edge. If you, as this thing is rotating around, if you walk towards the center, that's when you experience the Coriolis force. So what is this? We'll take a look at what this looks like. And then the transverse force is if you're standing at a given location and then the rotation rate changes. So you're standing in a given location on a merry-go-round like this, and here's where it's rotating like that. And then all of a sudden the rotation stops, then you will feel yourself being accelerated in some particular direction simply because you were already moving in that straight line, but you chose a coordinate system that had the center, where pointing towards the center was, north or whatever. You chose a coordinate system that was attached to this rotating frame. When that rotating frame stops, then you feel yourself accelerated in a particular direction, when in fact, you were moving in a straight line, and then all of a sudden your coordinate system changed. So that's the transverse force. So the Coriolis force is, let's take a look at, say you're on the North Pole. Here's the North Pole. As you move from here, the Earth is rotating in this direction. As you move from here to a place that's closer in towards the North Pole, what's going to happen? Well, here you're moving with some speed. Here, halfway up, you're moving with half the speed. By the time you get to the North Pole, you've got no speed in that particular direction. So the step that you make from the equator towards the North Pole is, at the equator, you have to go all the way around that circumference in 24 hours, which means you're moving with some tangential velocity. As you move towards the North Pole, that tangential velocity is going to get less and less and less. And so you have this tangential velocity that's changing, and you say to yourself, oh, my tangential velocity is changing. I must be experiencing a force that is pushing me in a particular direction. That is the Coriolis force. So you feel, as you're moving from the equator to the North Pole, you feel yourself being accelerated so that your tangential velocity decreases all the way to 0 by the time you get to the North Pole. This is the thing that causes certain objects to rotate in particular directions. So let's say you have air that is moving from the equator towards the North Pole. That air is going to be accelerated in a particular direction relative to the North Pole. It's actually going to be moving in a straight line, but it's going to feel like it's accelerating towards the North Pole. And as a consequence, it's going to push things in this particular direction and cause them to curl around. If you have, on the other hand, if you have air that is coming in away from the North Pole down towards the south, it's going to feel a force that is accelerating it in this direction because the ground is moving in that particular direction, and it's going to cause things to circulate the opposite way. So when you have something moving from the equator towards the North Pole, it's going to accelerate in one direction. If it's moving from the North Pole to the equator, it's going to accelerate in a different direction. And then you just take a look and you say, all right, which way does the air flow from the pole towards the surface, and how is that going to cause things to spiral? How's it going to cause storms to circulate relative to the ground? So in the northern hemisphere, when storms are circulating, they're going to circulate counterclockwise. And in the southern hemisphere, you basically flip this whole thing over. So you have some object that's spinning like this. You have an object that's spinning like that. If you then take that thing that's rotating and you flip it, so it's rotating like this, and then you come to the other side and it's rotating like that, it's going to change from clockwise to counterclockwise. Let me show you exactly how awesome this is, or what I mean by that. So I'm going to switch this view. So let's see. I need an object that I can rotate. What's a good object to rotate that you'd be able to see? How about a salt shaker? Here we go. So here's a salt shaker. I'm rotating it like this. So let's see. Okay, here we go. So I'm spinning this salt shaker in this particular direction. You can't even see that. So let's try this one. Here we go. Here's a pen. Here's the pen. It's rotating in a particular direction relative to you. And then if I change, I keep rotating in the same direction, but I flip it around. Now it's going to be rotating in the opposite direction. So like that. This way is, according to you, is going to be what? clockwise or something like that. And then if I keep rotating and I flip it around, it's going to be going counterclockwise. So you can do the same experiment. You just take an object, you rotate it in some direction, you keep spinning in that direction, but then you turn it around and look at it from the bottom. It will be going the opposite direction, which means that the Coriolis force is going to be moving in the opposite direction. So things that are in the northern hemisphere that rotate one direction, in the southern hemisphere are going to be rotating in the opposite direction. All right, so those are these fictitious forces that arise from a rotating coordinate system. But of course, there is no rotating coordinate system in real life, at least not in Newtonian dynamics. And so for the case of gravity, you have gravity that's pointing like this. It's always going to be pointed towards the center. And so you're going to get centripetal acceleration that's going to cause you to orbit around the center. And there you go. That's what it is. Now, there are a few consequences of this. The fact that an object is moving around the center that you can get from energy, for example. You can say that let's see. The question is that similar to the way water goes down the hole in like the bottom of the sink in the northern and southern hemisphere? So if you have a completely stationary, disturbance-free fluid in a tub, in a pool like this, and you open up the drain, it will spiral in one direction in the northern hemisphere and another direction in the southern hemisphere. That is assuming what I mentioned, that it's completely still. There's no external forces acting on it. There's no local currents acting in it. There's no sound waves really propagating through it. It turns out, however, that it doesn't take much to break up the Coriolis force. And so, because remember, the Coriolis force is r dot omega. So it takes a fairly large change in radius in order to really see the Coriolis force in all of its power and glory. And so small eddy currents that are left over from filling it, any disturbances going around, a butterfly flies across and causes disturbances, all of these things can actually affect the direction that it rotates. So in general, the rotation rate that you get, the rotation that you get for stuff going down the drain is random. That's because there's a bunch of random disturbances that are happening. In principle, there's a slight preference for things rotating in one direction versus another in the northern and southern hemisphere. This shows up in tornadoes. Tornadoes primarily rotate in the northern hemisphere counterclockwise and in the southern hemisphere clockwise, but you can get occasional counter-rotating tornadoes in either hemisphere. And so some fraction of the time, a tornado will rotate backwards. So when you get things that are the size of tornadoes, that's when you can start to see the preference for one rotation direction over another. When you get to hurricanes, that's always the Coriolis force. Hurricanes are way too big to not succumb to the Coriolis force because they span a very large range in their distance from the North Pole. Let's see. Anything else on gravity? So this gives us also to Kepler's laws. We can use the force of gravity to predict the motion of something. So that says that the mass times the acceleration is equal to gm big M over r squared. The acceleration that you get when you're center seeking. So what does the acceleration look like when you're being accelerated toward in a circular motion like this? That acceleration is the square of the velocity over the radius, v squared over r. Okay, so then I just plug that in. mv squared over r equals gmm over r squared. So that's the mass times the acceleration, the circular acceleration, compared to the force of gravity that's causing it. The masses all cancel, and I get v squared equals gm. This r comes up there over r, which is interesting because this says what? This says that the square of the velocity, that's the kinetic energy, is proportional to the square of the velocity, is equal to the potential energy. Kinetic energy and potential energy are shared in this thing because one, you have a gravitational field and you have an object moving the gravitational field, and this is the potential that you get for the gravitational field, and this is the energy that you have from kinetic energy, except that there's a thing missing from the kinetic energy, and that's the 1/2 m. So if you put the m there, it means you have to put it on this side, and that gets you from the potential version of the kinetic energy, just the velocity field of the kinetic energy. Put an m to it, that couples your mass to that velocity. And then you couple the mass to this side, and that gives you the potential energy. So the kinetic energy is related to the potential energy. What a surprise that in a system where you have a bound object that is moving around, that the potential energy and the kinetic energy would be related to each other. So let me come back to this, answer some of these questions. If a tornado crosses the equator, it will break down. Yeah, so if a tornado were to cross the equator, you don't get the weather patterns that you need to form a tornado at the equator, because the equator, you have upward moving, the prevailing direction of the wind is upwards at the equator instead of across the surface. When physicists get funding to do cool stuff, where does the funding of the experiments come from? So when a physicist is doing experiments, it can come from a variety of sources. Some of it can come from like the Commerce Department through the National Institute of Standards and Technology. If you're measuring a fundamental constant, that will typically come through NIST, which is run by the Commerce Department. You can have NASA can pay for things. You can have the Department of Energy pay for things. The National Science Foundation can pay for things. Those are the main funding agencies. Let's see. A soccer player making a goal, shooting the ball with the effect the ball curves in the right direction. So in that case, what happens with a soccer player when they bend their kick is that you're actually creating an aerofoil. You're creating a high pressure side of the ball and a low pressure side of the ball, because you get the ball starts spinning and it will drag air around one direction more than it does the other direction. And so you get a low pressure on one side and a high pressure on the other side. This is stuff that's in the next chapter. Like fluid flow is the next chapter. So then you can create a pressure imbalance that will cause the ball to curve in some direction. So this is the ball from a soccer kick that curves. And same thing with a baseball that curves is not a Coriolis force effect. It's a fluid dynamics effect. Okay, so this is where we got to. We have the kinetic energy is related to the potential energy. Velocity is going to be how fast it's moving around this particular direction. That's related to the distance that it orbits. The distance is going to be a that it orbits. And so what do you end up with? You get like 2 pi a over r. 2 pi a over the orbital period squared, that's the velocity squared, is equal to gm over r. And then I rearrange all these things. 2 pi r, like this. 2 pi r is the circumference of the circle. You do it in one orbital period. So 2 pi r over p squared, that whole quantity squared, is gm over r. And then I just rearrange things, and I'm going to get Kepler's law of planetary motion. So what do I have? I've got 2 pi r over orbital period squared is equal to gm over r. Rearrange all this stuff. This r goes up there. The gm goes in the denominator, and I get p squared equals 4 pi squared r cubed over gm. That's Kepler's law. That's the relationship between the orbital period of an object and the distance that it orbits from, in this case, the sun, but it's whatever it is that it orbits. It's going to have this p squared equals the orbital distance cubed. So there you go, Kepler's law right there. All right. Any questions on this stuff? Anything else that's happening? There are a couple other Kepler's laws that are related to this. This is Kepler's third law, is this one. Kepler had two other laws of planetary motion, so objects in motion in a gravitational field. One of his laws says that orbits are ellipses. Which is not completely true. It's slightly different than that. And the second one is that a line connecting the star and the planet sweeps out equal area and equal time. So you have, for Kepler's three laws, you have his first law is the law of ellipses. What this should actually be is that the real statement is that an orbit of an object around another under a gravitational field is that you get a conic section. The second one is equal area. That says that a line connecting the center of mass of the system to the object as the object orbits around is going to sweep out an equal area in an equal time. This is a statement of conservation of angular momentum. So angular momentum is conserved, and as a consequence, when you shorten the distance, you have to speed up the motion of the object, such that the area is proportional to the distance and the speed that you're sweeping out. And so that has to stay the same, right? So you have some orbital distance that you have, and you have some rate that you're sweeping it out. And so if that's conserved, the angular momentum is basically this, that the angular momentum is related to the distance that you're orbiting and the speed that you're orbiting around. And so if you change one, you have to change the other, so that the quantity, the angular momentum quantity has to be the same. Angular momentum is actually mr squared times omega. So the angular momentum of an object orbiting around another is written like this. And so if one of those things goes up, the other one has to go down. If the radius gets bigger, then omega has to slow down. Omega is the rate that the rate of your orbit around the object at a given time. So if the distance gets bigger, then the rate that you move has to slow down to keep this thing constant. And your distance gets smaller, then the orbital speed has to speed up. So let's take a look at this real quick in a little bit more detail. And then the third law is the one that I just showed you. The third one is that p squared equals a cubed. This is conservation of energy. Okay, so energy is conserved, and also it's the relationship between the kinetic and the potential energy in a bound orbit. So that's p squared equals a cubed. Energy is conserved. Equal areas is angular momentum is conserved. The law of ellipses is basically, it's actually that things form conic sections. That tells you that the gravitational force goes as 1 over r squared. And anyway, so there you go. Real quick on this one, the angular momentum, you have m times, well, let's see. What is the area that you have that you sweep out? So here's your central object. Here's your other object that's moving this way. It's going to sweep out some area, some little triangle in a given amount of time. That's going to be this motion. That's r times the angle that you sweep out, which is r omega. And then that distance r. Whoops, distance r. And so the area here is r times r omega. And so that's your r squared omega. And then you just add the mass in there, and that gives you angular momentum. All right. Okay, let's see. Examples. Let's see. What's greater than pi? 2 pi over r. Anyways, Kepler's laws, they're just a natural consequence of the conservation laws that were described earlier, or conservation laws that we've already gone over. So they're not as groundbreaking given the order that we presented the material. They're not as groundbreaking as they were 400 years ago when Kepler described them. All right. Any other questions? So the plan will be on Tuesday. I'll be back. On Tuesday we'll be going over fluids. So that should be interesting. Tuesday's going to be fluids. Next Thursday there's no stream, and then the Tuesday after that we'll continue on with whatever it is that we're talking about. So should be pretty good. Pretty interesting content. Kepler's second law is a qualitative statement. Kepler's second law is a quantitative statement about the conservation of angular momentum. So you have angular momentum in a system. That angular momentum is I omega. So omega is the rate that the thing is rotating. Right. This is the coordinate that is changing, is the angle, and I is the moment of inertia. The moment of inertia is mr squared, and omega is the rate that the thing is advancing. So you just rearrange this to get mr omega times r. This r times omega is mv. Right? That's instantaneously mv, and this is the distance. So in a given second, because angular momentum is conserved, this says that a little piece of area in like 1 unit of time, a piece of area is going to be mvr, right? So you have 1 unit of time, and so velocity times time gives you a distance, and so that will, so if I basically multiply this by time, mvr times time, then that gives me a triangle. Okay, and if I lower the distance down, then the velocity will speed up. Angular momentum conservation says that if I lower the distance, the velocity has to get bigger. So if the velocity has to get bigger, then that means that this omega has to get bigger. If I increase the distance, then the velocity has to get smaller. The only way for the velocity to get smaller is if omega gets smaller. And omega has to get smaller faster than r because you have 2 r's that you have to overcome. And then the fact that, so mvr is conserved, that's angular momentum right there, it's conserved with time. And so the area that you sweep out in a fixed amount of time, so you have a fixed amount of time, the area that you sweep out is some roughly triangle-shaped thing. and that's going to be independent of time. So it doesn't matter. So it's independent of time, and if you change one of the distances, angular momentum conservation, which is this quantity, has to accommodate for that change. So the Zagreb-Blankov effect or tennis racket theorem works the same way in the space station, on the space station. Oh yeah, okay, so that's an interesting thing about rotating reference frames. So that's a slightly different thing. So that's an object that's spinning in space. We didn't actually go into that. That could be an interesting thing to discuss. All right, so let's do it now. When you have some blob, here is your blob. It's going to have, the mass is going to be distributed in a particular way, and in 3 dimensions, you're going to have so there are 3 dimensions, there are 3 coordinate axes that you can choose to represent this blob. So you could have a coordinate system that looks like this, and you have this blob that's in that coordinate system, or you could choose coordinate system that is more natural to this blob, okay? So for example, if I had a blob that looked like this one, it might make more sense to have a coordinate system that looked like this. That's quite the ugly coordinate system. You have a coordinate system that looks like this. Okay, so that one axis is, you have like most of the mass is in a particular direction, so that's one axis, then you have a different amount of mass in a different direction, and you slice it up so that the symmetry of the object is related to your coordinate axes. So you choose a coordinate system where the symmetry of your object, or the distribution of your object, more naturally fits with that coordinate system. So for example, if you have a sphere, it doesn't matter. Sphere, you can have the coordinate system any way that you want. But if you have a prolate spheroid, like this, so here's a prolate spheroid, it would make sense to have one axis going through, like a watermelon, so here's a watermelon. It makes sense to have one axis going through the long way, and then the other 2 axes you can kind of choose which direction you want them to come out. If you have a bar of soap, so a bar of soap is a triaxial spheroid, where it kind of, oh, it's kind of ugly. So a triaxial spheroid is one where it's got a thin axis, a thick axis. The cross section is elliptical, and then it has this long one. So then you would choose one axis that goes this way, one axis that goes this way, and one axis that goes this way. So this one goes through it in the skinniest part, this one goes through it on the longest part, and this one goes through halfway between the 2. So with any mass distribution, you can devise these principal axes. Okay, and what ends up happening is that if you have, if you rotate around, so now you assign a coordinate system that's based upon the principal axes, like what's the most natural distribution of the material. If you spin around the axis that has the largest moment of inertia, so that would be that if you have, okay, say you have an iPhone case like this. So this has 3 different axes. Let me pull up just the camera. Okay, so here's my iPhone case. It has 3 principal axes. It's got the long axis like that. It's got the short axis like this. So that's the rotation around the short axis. And then it's got the intermediate axis, which is that one, which would be like that, like yay. Now it turns out that if you rotate around the smallest axis, that gives you the largest moment of inertia. So here's the largest moment of inertia. If you rotate around the skinniest axis, that gives you the smallest moment of inertia. And then the one in between, if you rotate around this axis, that gives you some intermediate moment of inertia. And if you compare, you compare 2 different surfaces. One of them is the energy surface, how much energy you have with a given rotation, and the other one is the angular momentum surface. I think those are the 2 different quantities. Ellipsoids of constant L and T, yes. So here's the diagram of it, right there. What this says is, at a given rotation rate, you have angular momentum that's a conserved quantity, and you have energy that's a conserved quantity. And so if you have, at a given rotation rate, you're going to have a maximum amount of energy. Okay, if you're going around the small axis. If you're going around the long axis, then you're going to have a minimum amount of kinetic energy and a minimum amount of angular momentum. And then if you're going around the intermediate axis, then you're going to have an intermediate amount of both. But if you look at these surfaces, it will look like this. Where did my pen go? I can't believe this. My writing utensil is missing. Well, now that's crazy. Here it is. What you have is, here are your three principal axes, like this. But I pull this back up. Here are your three principal axes. You have one surface that is your energy surface that's going to look like this. And then you have another surface that is your angular momentum surface. So your surface of constant angular momentum is going to look like this. So if you orbit around one axis, then, so how does this work? I haven't done this for a long time. Okay, hold on. I drew this wrong. Okay, so if you're rotating around the short axis, then you get, so here's your three axes. You have a line of, or you have a shape, or it's like this ellipsoid of constant angular momentum, and you have ellipsoid of constant energy. And those are going to meet like this. So you have an energy surface. Actually, the angular momentum surface is going to go as omega. The energy surface is going to go as omega squared, and they're going to meet at a single point. And that's going to give you a stable result. If you rotate around a different axis, then you're going to end up with this ellipsoid going in this direction, and they're going to meet here at a single point. So you have one single point that simultaneously has the rotation that you're looking for and the angular momentum that you're looking for when you're spinning some object. The same thing is true in the other axis. For the third axis, what you end up with is you get a line where these two things intersect each other. The one interior to there and the one exterior intersect each other, which means that your object can spin anywhere along that line and conserve both energy and angular momentum. And so because of the fact that it can spin anywhere along that line, it will spin anywhere along that line. And it will flop around going from one configuration to another. So that's this Jabzinskov effect. That's the reason why if you throw up a deck of cards, for example, or a skateboard, it will flip. If you're spinning it around a particular axis, it will flip in a funky pattern where it will both spin in one direction and rotate in a different direction. All right. One other thing that is kind of interesting about rotation, and since the Olympics are going on right now, I might as well discuss this one. So this is another aside, is how does diving actually work? So here's a diver, here's the Olympics, you have a pool down here, the diver is up here on this platform, stands like this, jumps into the water, and somehow magically is able to spin this way and spin this way, starting from a stationary thing, but then they can unspin one of those directions. So for example, you'll have a diver who will jump up, go into some kind of pike position or something like that, spin around the vertical axis going through their head, and then come back out of it and then stop spinning in the vertical axis, in the vertical direction. So they'll go through like a thing with a twist. They'll jump up, go into a pike position, they'll twist around once, and then they'll stop spinning. The same thing happens with aerials in the Winter Olympics. So if we look at Winter Olympic aerials, I spelled it wrong. Top 5 freestyle skiing aerial flips. So when you look at people doing aerials or doing diving or in gymnastics doing the same thing, they'll go up, okay, and so now the person is spinning in both directions. Here it goes, ready? So they're coming in straight, go up, and he's going straight, he's still straight. He's gone up, I'm assuming this is a man, it could be a woman, David Morris, so that sounds like a man. He's spinning straight, his feet are coming over, and then he's going to do something weird. He's going to do something with his arms, and he's going to start rotating sideways. There's his rotating sideways. I can slow this down to make it even more cooler. So he's rotating sideways, and then he's going to stop. Then they're going to do this weird flash that's going to get us out of this. So let's take a look again as he does it. He comes in straight, perfectly straight. I don't know why they keep doing this flashy thing. And now he's spinning sideways. Pulls his arm in to spin faster, spinning sideways. And then he's going to come back out and he's going to stop spinning. At this point, he's only rotating head over heels again. Okay, so he's spinning around his head. And then he's going to come in. And at this point, he pulls his arms back up again in roughly the same position that he launched from. And he's going to only be spinning head over heels, and he's going to land going straight again. So somehow he's flipping head over heels, going straight, and then he starts spinning sideways, and then he lands again, going straight. And that is, how does this happen? How does he conserve angular momentum? There's no forces acting on him. Once he leaves the launch pad, or once he leaves the ramp, he's going perfectly straight, arms up, and then weird flashy thing to make it look even cooler than it probably really was, or even, I guess, to get in the way of how cool it was, as if it wasn't interesting enough to watch the person go. We have to add these flashes in, but never, no matter. And then he comes in and lands perfectly straight, no problem. Where did all this spinning come from? How do you know, where's the torque that's causing the angular momentum to change? The answer is there's no torque causing the angular momentum to change. Here's what's going on in that case. You start with a person. They are standing up like this. Here's the person, arms up in the air. Okay, so that's kind of an ugly person. Let's try that one more time. Here's the person, like this, arms up in the air, like that. They are going to spin around this axis, where their feet are going to go that way and their head is going to go that way. So then what's going to happen is that person is going to change from this position to this position. Okay, so they go up like this, and then he moves one arm down to the side. What is this going to do? So now the moment of inertia has changed. What this is going to do is it's going to shift the person to that side. So they're not actually, when they pull their arm down, they're actually, their body is going to rotate. As this arm rotates down, their whole body is going to compensate for that rotation by rotating in the opposite direction. So this is not actually what happens. When he moves his arm down, he's actually going to be like this. Okay, his arm is down and he's going to be tilted over sideways. Now, he's still flipping over along this line, but his whole body is shorter. Like his mass is distributed and his in over a shorter distance. So he's pulled mass in. It's changed how his mass is distributed, and so his body has to compensate for that somehow. There has to be conserved angular momentum, and we've just changed his moment of inertia. So his moment of inertia has gotten smaller as he pulled his arms in. So in order to, we have a total angular momentum that is his moment of inertia times his rotation rate. But there's two kinds of angular momentum in the system. There's angular momentum around this axis, and there's angular momentum that he can have around this axis. The angular momentum that we care about is the one around this axis. That's the one that has to be conserved, right? Because that's how he started. He started with angular momentum only around that axis. And so that angular momentum has to be conserved. When he shortens himself around that axis, what can happen, now he's got a component of his angular momentum around this axis that goes through his head. A component of that direction is now aligned along this, his original direction. So let me try that one more time. He starts off, all of his angular momentum, well, and this is going to be the case all the time, his angular momentum is along this particular direction, and his mass is going to be distributed perpendicular to that direction. When he puts his arm down, here's the direction of the angular momentum that we have to conserve, but now he's tilted to the side, like this. He's tilted to the side, and so his rotation around this line is now in the same direction, or has a component that is in the direction of his original spin. So here's his angular momentum. Now that he's tilted himself to the side, he can rotate now around this axis, and it will contribute to the angular momentum around that axis because those two directions are no longer perpendicular. They started perpendicular. The axis going through his head, it was originally perpendicular to the axis around his waist, or that goes through his waist. When he moves to the side, now the axis going through his head is no longer perpendicular to the axis going through his waist. And so he's going to start rotating in that direction to add angular momentum in this direction. And so he will start to spin. When he moves his arm to the side, that will cause him to start spinning around the axis that goes through his head. And then in order to stop that, he has to put his arm back up. When he puts his arm back up, he straightens back up again like this, and his rotation around his head stops, and his rotation around his waist is the only thing that's left over. So that is what's going on. When someone starts to spin in air, they will move their arms to change their moment of inertia, which will cause them to tilt relative to their the axis that they're rotating around, and that will allow them to spin in this direction and conserve angular momentum in its entirety. It wasn't a very good explanation, but that's what's going on. At some point, maybe I should do a. It really would take an animation to do a good job at this. But anyways, there you go. That's how the Olympics work. That's how diving works, how gymnastics works, and how aerials and moguls work. It is a lot of linear algebra, basically. You have a structure in a given coordinate system. You're spinning around one of those coordinate axes. Then you change the orientation of that structure, which now means that there's a component of a variety of different things that are in the original direction. And so you can spin around any of those component directions as long as the sum keeps your angular momentum in the original direction. Then if you want to get back to rotating in the way that you were originally rotating, you have to move your mass back to the way you started from and land. And so that's this landing right here. He nailed his landing. There's probably going to be another one. There's some where they come out. They'll go into a twist and then they'll come back out. But if you were to look straight down the line, like straight down the attack where they're coming in, you'll find that their body leans over to the side as they're doing the spins. So they go up and they're spinning in a particular direction, and then their body will lean to the side as they're twisting, and then it will come back up straight again when they get to the bottom. Speedy. So then he's going to up like that. He's going to be going slightly to the side. And then he lands. You can see this also that he's going slightly to the side just by looking at where the skis are. Because if he was going straight head over heels the whole time, then you would never see the bottom of the skis. So let me speed it up a little bit. You'd never see the bottom of the skis. And you can see the bottom of the skis right there. So if he was always spinning head over heels, then you would never see the bottom of the skis or the top of the skis. But the fact that you can see the bottom of the skis means that he's actually tilted slightly to the side, which is what allows him to spin around. Yeah, so the momentum from one axis, well, so there's two different coordinate systems to consider here, right? There's the coordinate system of the observer. Coordinate system of the observer looks like this. The coordinate system of the person is this. You've got one axis here, one axis there. And the coordinate system of the observer is fixed to the observer. So what happens is the person will spin around their waist or around their head. And when the person, but the momentum, the angular momentum of the original flip is in the coordinate system of the observer from the outside. So you have the skier, here's the skier, the coordinate system of the skier, the coordinate system of the camera, or the coordinate system of us is out here. And the angular momentum of the skier initially is in this direction. And that's all along the skier's waist, or like on the line going through his waist. When they tilt to the side, it's the angular momentum out here. It's the angular momentum to us, to our coordinate system that is conserved. when they tilt to the side, they are rotating in our coordinate system. And so their body is going, and that's where the angular momentum needs to be conserved, is in the outside coordinate system. When they tilt themselves to the side, then they can start spinning in this direction, provided that that rotation contributes appropriately to the angular momentum in the outside coordinate system. And then when they're done, they rotate themselves back into the reference frame of the outside observer. Anyway, so that's how that works. Okay, so next time we will start with fluids and do thermodynamics and fluids, which is basically all the stuff that we've done to this point, adding gravity to the mix, and seeing how it changes when you go from point-like particles to continuous media.